Hi everyone, we are Group 18 and our project is GPMS, a Generative Projection Mapping System. Welcome to our final demo.
My name is Francisco and I am a computer engineering major. Declan and Victoria are also computer engineering majors. First, we will run through a GPMS parts overview, which will include all the parts and subsystems within our project. Next, we will show you our project demo. Finally, we will show you the engineering requirements that our project will adhere to, and we will emphasize 3 of those requirements that we have demonstrated to you in our demo.
GPMS is your Generative Projection Mapping System. GPMS is a system designed to transform any physical structure into a canvas for AI-generated art. It consists of Raspberry Pi 5 connected to a touchscreen display, projector, and camera. The user starts by calibrating the projection area via software and aligning the projector's field of view with the target structure, as shown in the animation above. Once the alignment is complete, the system captures an image which is then sent to our custom generative AI server. The server processes the image and generates a stunning AI image that aligns with the key vertices and edges of the captured structure, as demonstrated in the animation below.
To assist in hardware integration and better provide portability and compactness to users, we decided to include a hardware subsystem enclosure designed using CAD tools and 3D printed using PLA filament. This enclosure is mounted and fastened on top of the projector using Velcro in order to avoid any instability. It houses the touchscreen monitor, Raspberry Pi 5, and camera module. All the cables that run from the Raspberry Pi are the micro HDMI to HDMI for monitor image data transfer, micro HDMI to HDMI for the projector image data transfer, Ethernet for API connection, USB-C for Raspberry Pi power supply, and USB for monitor to Raspberry Pi touch/data transfer, which are all concealed completely in order to free users of any cable clutter that may disrupt their engagement with GPMS. On the top, the touchscreen monitor sits flush like a phone in its case into the enclosure at a 13-degree angle for users to interact with while avoiding the glare. Then, the monitor's HDMI and USB ports connect to the 90-degree angled adapters, which then connect to the Raspberry Pi 5's respective ports in the open space layer below it. Then, the Pi connects to the camera module via serial camera interface, parallel on the same plane as that of the projector lens. This camera is intact, screwed into the front face of the enclosure in order to remain static and avoid unwanted movement. Here, we will present the GUI, which is what the user will interact with at the click of a button. We will walk you through the entire process for each page of the GUI here shortly. Here we present OpenCV and Stable Diffusion and how they both work alongside each other in GPMS. Together, they work to capture, process, and generate images based on a structure. The device will first use OpenCV to capture a structure via camera to detect the features of that structure and then allow a user to input a creative prompt into the deep learning model, Stable Diffusion, describing how they want that structure to be transformed. Stable Diffusion uses this prompt to generate an image based on the detected structure, projecting the prompt's elements onto it. The final result is a combination of the original image structure and the artistic transformation. The server sits in the Draco lab here at UCF, located in Engineering Building 1, Room 263. This is where users will send text prompts via our GUI and receive a selection of AI-generated images. Our API module opens a designated port on a Python server to handle post requests from users to the server for AI image generation. It accepts a prompt, which is the user's vision, and an image capture, which are processed via OpenCV from the user's structure selection. Then, Stable Diffusion is used with control nets to generate the AI images. The control nets ensure that the generated images respect the structure of the input image while also incorporating the user's prompt. The server processes the request and returns a selection of AI-generated images to the client, providing multiple variations based on the input.
Dude, what time is the party supposed to be at?
It's at 7. Why? Dude, it's 1:45.
Did you get the decorations?
No, I thought you did.
I told you to get the decorations.
No, you didn't.
Yes, I did.
Guys, I have an idea.
Picture this. It's the night of your Christmas party. Your apartment looks, well, ordinary. Those sleek modern art pieces that usually fade into the background aren't exactly screaming festive. You want your space to dazzle, but time's ticking, your artistic skills are questionable, and you're craving a high-tech solution. Enter GPMS, the Generative Projection Mapping System, a system designed to transform any physical structure into a canvas for AI-generated art. Imagine turning your entire living space into a winter wonderland in less than a few minutes. Step 1. Setup. First off, set up the projector and connect it to the GPMS device. With the projector on a table or tripod, place GPMS on top of the projector and plug in both items. This is your canvas for creating holiday magic. Now, begin navigating the GUI by first reading the instructions on the main window. Step 2. Projection area calibration. Next, calibrate your projection area using the GPMS software. Simply tap each corner of the projection space to set initial markers. For precise alignment, press and hold any corner until the magnifying glass appears. Then, drag to exactly match where the projected corners meets the surface. This calibration process creates a digital canvas, defining the exact boundaries where the GPMS can project your designs. Step 3. Adjust threshold values. Here's where you can fine-tune your decoration. We'll adjust the threshold values and observe changes in edge detection. This step determines how closely the new image will match your room structure. Want your decorations to follow the lines of your existing art, or prefer them to be more freeform? You can control that here. Step 4. Input your vision. Time to tell GPMS what you're dreaming of. For our Christmas party, we might select the style to be realistic and, using the on-screen keyboard, input the prompt Santa in a dark forest. This is where you can let your imagination run wild. Step 5. Generate and refine. GPMS will now generate a series of images based on your input. Don't love what you see? No problem. You can tweak your text input, adjust the sensitivity thresholds we mentioned earlier, or recapture the structure. Keep refining until you find the perfect holiday look. Step 6. Project and enjoy. Found an image you love? Great! With a simple click, we can now project it onto your space. Just like that, your room is transformed into a winter wonderland ready for your Christmas party. GPMS is a versatile tool for any occasion or mood, whether it's a spooky Halloween gathering, a summer beach party, or just a cozy night in. GPMS can help you set the perfect scene with ease. As you can see, we have several categories of specifications. Size. Our target dimensions are 7 by 10 by 8 inches, ensuring the device is compact and portable. Weight. We're aiming for a weight of less than 10 pounds, making it manageable for users to handle and transport. While these specifications are important for the overall design and usability of our device, today we'll be focusing on measuring and discussing the last 3 specifications highlighted in yellow. First, elapsed time. Our target is less than 5 minutes for the entire process. 2. Alignment accuracy. We're aiming for less than 8 millimeters of offset from our projected image. 3. AI generation time. Our goal is less than 1.5 minutes per image. These 3 metrics are crucial for ensuring the efficiency, precision, and speed of our GPMS device, which directly impact the user experience and overall performance of the system.
Our first metric is elapsed time, with a target of less than 5 minutes. This measures the total time from setting up the device to projecting the final image. For this demonstration, we've conducted 10 test runs, recording the elapsed time for each. Our test procedure involves starting a timer, setting up the projector and GPMS device, calibrating the projection area, adjusting threshold values, inputting a vision prompt, generating and selecting the final image, and projecting it. As we can see from our results, the individual run times ranged from 1 minute and 13 seconds to 1 minute and 37 seconds, with a mean time of 1 minute and 24 seconds, excluding AI generation. The standard deviation was 7.64 seconds, indicating consistent performance across runs. When we factor in AI image generation time of 3 minutes, our mean elapsed time increases to 4 minutes and 24 seconds. This is still within our target of less than 5 minutes, demonstrating that we're meeting our specification for this metric. Our next metric is alignment accuracy, which measures how precisely we can align the projected image with the target surface. For this demonstration, we conducted 10 test runs. In each run, we measured the alignment accuracy at 4 points on the projection surface, recording the deviation in millimeters from the ideal position. Looking at our test results table on the right, we can see the individual measurements for each run. The accuracy for each run, shown on the left table, is calculated based on these 4 measurements, with lower numbers indicating better accuracy. Our target is to achieve an accuracy better than 8 millimeters for each run. As we can see from the average accuracies column, all of our runs met this target, with average accuracies ranging from 0.75 millimeters to 2.75 millimeters. The average accuracy across all runs is 1.725 millimeters, with a standard deviation of 0.6175 millimeters. This indicates that on average, we're significantly outperforming our target of 8 millimeters, and our performance is relatively consistent across runs, as seen by our standard deviation. These findings provide a solid foundation for precise image projection in our system, meeting and exceeding our initial expectations. Our last metric is AI generation time, which measures how long it takes for our AI model to generate a single image and return it. However, it's important to note that at this stage, we only have data on the time it takes to generate the image, not the time to send it back to the user. For this demonstration, we conducted 10 test runs, measuring only the AI's image generation time. Our target is to generate each image in less than 1.5 minutes. Looking at our results, we can see that our generation times for each run range from 42.6 to 43.4 seconds per image. The mean generation time across all runs was 42.9 seconds, with a standard deviation of 0.23 seconds. These results show that our AI generation times are significantly faster than our target of less than 1.5 minutes per image. The low standard deviation indicates that our generation times are highly consistent across multiple runs. Thank you for listening to our presentation. For more information, visit our website.